Hello everyone. What I want to do in the next two videos is finish up the basics of compound interest. And in particular, what I want to do next is talk about nominal interest, which is a very common way to describe interest rates when you have a compounding period other than 1 year. All right, so let's just dive into the definition of nominal interest, and then I'll immediately do an example after I present the definition. So let's suppose I'm given an integer m, a positive integer m, and let's suppose I'm given a rate I superscript m. I want to emphasize this is not raising anything to the power m, this is just standard actuarial notation, so I'm fairly obliged to use it, even though it does look like you are taking something to the power m. Okay, so the definition of this rate I superscript m is that the interest, the actual interest for a compounding period of 1 over m years is I superscript m divided by m. Okay, so let's dissect this definition a little bit. That tells me that the growth factor for a period of 1 over m years is 1 plus I superscript m divided by m. Okay, well there's 1 over m year periods in a year. So if I compound this growth factor m times, I get the 1 year growth factor. If I compound this growth factor m times, I mean you just multiply by itself this 1 over m year growth factor m times, and that's just obviously 1 plus I superscript m over m to the power m. Okay. So let me do an example if this is a little abstract and fuzzy. So let's say we have nominal interest of 5.2% compounded weekly. Okay, so I'm not explicitly telling you what m is, but if we compound interest weekly, there are 52 weeks in a year, so that means m is 52. Okay, and so I superscript 52 is given by this nominal interest rate, 5.2% as a decimal 0.052. So by definition, the weekly growth factor is just 1 plus the weekly interest rate. And by definition, that the weekly interest rate is my I superscript 52 over 52, which is 0.001. And of course, a week is the same thing as a period of 1 over 52 years, or 1/52nd of a year, rather. Okay, and so we compound this 52 times to get the yearly growth factor, which is 1.05335. Okay, so one thing that is quite interesting about this example, and I would be very beneficial to remember this for not just this course, but for any course involving compound interest at all. Whenever you're given a nominal interest rate and you find the equivalent yearly interest rate, the two answers are going to be not very, but they're going to be relatively close to each other. Okay. And if they're not, then you did something wrong. So for example, if I gave you this as a homework and I said, well, nominal interest compounded weekly is 5.2%, find what the equivalent yearly interest rate is, and you got something like 10% instead of what's the correct answer is as a percentage 5.335, you just subtract 1 from the yearly growth factor, multiply by 100. So if you got 10% instead, you definitely did something terribly wrong, because 10% is not even close to 5.2%. 5.335% is fairly close to 5.2%. And the same thing is true going backwards. I'll give you a formula in a moment. If you're given a yearly interest rate, how do you compute a nominal interest rate? If you do that, the two answers better be fairly close to each other, or you did something wrong. Okay, and as I said, the equivalent annual interest rate is 5.335, and I just want to stress a term here that we're going to use throughout the rest of this course, and that is effective. When I say, whenever I have an effective interest rate, I mean an actual interest rate. The actual annual interest rate here is 5.335%, meaning you have, your fund grows by 5.335% each year. Whenever I say nominal interest, I mean by definition, here M is 52. So again, by definition, whenever I say nominal interest, in this example, I mean you're going to take whatever nominal interest you're given, divide, in this case it's 52, and that gives you, by definition, the weekly interest rate. The interest rate for a period of 1/52 years, which is 1 week, or rather 1/52nd of a year. Okay. Okay, so just kind of go over some formulas. Basically, remember, we just said, by definition, I mentioned this multiple times already, that if I'm given a nominal interest rate I superscript M, the equivalent effective interest rate J over a period 1/m years is I superscript M over M. And that means the equivalent yearly growth factor is, well, 1 plus I superscript M over M to the M. And you subtract 1 to get the equivalent effective annual interest rate. And again, I'm highlighting effective versus nominal because effective means the actual, 1/mth year-long interest rate is I superscript M over M. Saying this is a nominal rate just means that the effective interest rate J over this period 1/m years is given by this formula. And that means the effective annual interest rate, the actual annual interest rate, is given by this formula. Okay. Now you can go backwards, and if you are given the equivalent effective annual interest rate I, or for short, if you were just given the actual annual interest rate I, you could solve for I superscript M very easily. You just add 1, raise both sides to 1/m, subtract 1, multiply by M. And I encourage you to check that if you do that, you would get this formula here. Not terribly difficult algebra. Okay? So given I and given an integer M, the formula for I superscript M is as follows. Okay? So for example, let's take the previous example we did and just work backwards. Let's say instead we were given I was 0.05335. And let's say we were given M is 52. You would then plug into your formula, just plug and chug this here into a calculator, and then out would come the nominal interest rate compounded weekly is 5.2% or 0.052. And it should be fairly clear from the examples I did, but just to emphasize, these formulas give you interest, nominal, and effective annual interest, respectively, as a rate, as a decimal rather, not as a percentage. So for example, this gives me 0.52 as a decimal, and I plug in decimals, not percentages, And same thing here. I plugged in 0.052 as a decimal, not as a percentage, and it spit out a yearly growth factor, which subtract 1 gives me the decimal interest rate 0.05335. Okay, let's now look at what happens when M is really, really large. And that's a fairly realistic scenario. You might want to compute interest daily, which would be M equals 365. You might want to compute or compound interest hourly, which would be 365 times 24, I think it's like 8,000 something. You might want to compound interest, per minute, every second, et cetera, okay? And the nominal interest rate that we get when M gets larger and larger and larger, we denote by delta. You could denote it as I superscript infinity, but that's kind of weird to write everywhere. So we like to denote it by delta. And that's, by definition, this is just going to be, we're going to take this formula here, I superscript M, and let M go to infinity. And here we're given the annual interest rate I. Okay? We're given the effective annual interest rate I. All right, and I encourage you, if you're a math major, an actuary major, to try to do the L'Hopital's rule calculations. This is of the form infinity times 1. And if you correctly do this L'Hopital's rule problem, you'll get that this is natural log I plus 1. And so the idea here, really what this means is that, well, delta is basically I superscript M for very large M. It's an approximation. This quantity here is kind of a pain for M large. We can approximate it by ln of I plus 1. It's just easier to work with. And it's really close for M nice and large. And we can, we can take this formula here, delta equals ln of I plus 1, and just solve for I. We can raise both sides to the e to the delta is I plus 1, and subtract 1 to get I is e to the delta minus 1. And of course, as I said before, delta is I superscript infinity. Just literally writing or having, like seeing the formula e to the I superscript infinity would look really bizarre. So it doesn't look nice to literally have e to the I superscript infinity. So delta is delta is I to the infinity. And we say delta is nominal interest compounded continuously because it is, it's like you're compounding interest when M is larger and larger and larger, which means you're compounding interest at a smaller and smaller and smaller time interval, and it's almost continuous, if we're, like I said, it's 365 would be daily, times 24 would be hourly, that times 60 would be per minute, that times 60 would be per second. So as we keep going, it's almost like we're getting compounding continuously. Anyway, so let's do an example. Okay. So Fund A offers nominal annual interest of 7.1% compounded semi-annually, while Fund B offers nominal annual interest of 7% compounded daily. which option provides better yearly growth? And you definitely don't want to just say, well, 7.1% is larger than 7%. Obviously, it's got to be Fund A. No, let's actually compute the growth factors, or equivalently, the equivalent effective annual interest rates for Fund A and Fund B. Obviously, you just add 1 to get the respective growth factors. So finding the interest rates, if finding the 2 effective annual interest rates, it's basically the same thing. We want to figure out which one has a higher effective annual interest rate.
Okay, so for this problem, you certainly do not want to just say, well, 7.1% is bigger than 7%. The obvious answer is 7.1%. We really just have to plug into our formula and see which one gives us the better yearly growth. So let's write down the information for Fund A. So here we're compounding interest twice a year, so m equals 2. We're given nominal semi-annual interest, I2, is, well, 7.1%, so as a decimal, 0.71. So the equivalent effective annual interest rate corresponding to nominal semi-annual interest of 0.071 is just, well, just dump into your formula, nothing more than that. So it's 1 plus 0.0, sorry about that, 0.071 over 2, whole thing raised to the power 2 minus 1, and you get 0.0, let me move that over a bit. This is going to be 0.07226. All right, so let's go to another page for Fund B, and we'll compare the two. All right, so for Fund B, interest is compounded daily, so M is 365. All right, we're given that nominal daily interest is 7%, so this is 0.07. So again, plug into your formula for the equivalent effective annual interest rate. 1 plus I 365 over 365 to the 365 minus 1. So it's 1 plus 0.07 over 365 to 365 minus 1, and so that gives you 0.0725, which is larger than what we had previously. So this is 7.25%, this is 7.226%, so this is my answer. Fund B offers a greater yearly growth than does Fund A, even though the nominal interest for Fund B is smaller than the nominal interest for Fund A. I mean, you can't, like I said, you can't just literally look at these numbers and compare them. We're compounding totally different number of times. Fund B is 365 times a year. Fund A is twice a year.
I should mention that in this formula here, if I superscript M is fixed, let's say, for example, it's 5%, regardless of what M is. So it's just 5%. So we're just looking at I. Let's say we don't know what M is. Let's say we're looking at I equals parentheses 1 plus 0.05 over m raised to the m minus 1. Okay? This, as a function of m, is increasing. The larger m is, the larger I is, and you basically have a horizontal asymptote as a function of m, given by, well, as m goes to infinity, we get, the asymptote is exactly e to the delta minus 1, and in some sense, when m equals infinity, quote unquote, we do reach that, and by that I mean, given nominal interest compounded continuously, we get I equals e to the delta minus 1. Okay, so just something to think about. And so in this case, delta would be 0.05, so I would be 0.05 minus 1. So yeah, just something to think about. It is something to remember. If I superscript m is held constant, this here increases as m increases. Right. Okay, so let's do another example. Fund A offers 8% nominal interest compounded weekly. Find the minimal nominal interest rate compounded monthly that Fund B needs to offer to be competitive with Fund A.
Okay, so for this problem, let's first figure out what the effective annual interest rate, or the equivalent effective annual interest rate is for Fund A. So, and I'll explain why we're doing this in a second. So we're given that for Fund A, interest is compounded weekly. So that's 52 for M, 52 times a year. We're given that I, 52, is 8%. So this is 0.08. So for Fund A, the equivalent effective annual interest rate, just dump into your formula. 1 plus I, 52 over 52 to the 52 minus 1. 1 plus 0.08 over 52 to the 52. That gives you 0.08322. All right, so this is for Fund A. Okay, so for Fund B, well, what do we know? We know that interest is compounded monthly, so that corresponds to 12 times a month. And we don't know what I-12 needs to be, and let's figure it out. And what we're going to do is we're going to find the monthly nominal interest rate that gives me this yearly growth here. Because if we pick for Fund B any smaller nominal interest rate, then we're going to have smaller yearly growth than Fund A. We want Fund B to have competitive yearly growth to Fund A. So we have to find the nominal interest rate I-12 that corresponds to the same yearly growth that Fund A offers. Okay, so how do we do that? Well, we just plug in for I equals 0.08322. Okay, so that means I-12 is going to be 12, plug and chug, 1 plus I, 0.08322 to the 1 over 12 minus 1, and that gives me 0.0802. Okay, so again, the practical meaning here is if Fund B offers any smaller monthly nominal interest rate, then the yearly growth of Fund B is going to be less than the yearly growth for Fund A. So to stay competitive with Fund A, we assume Fund B offers the same yearly growth as Fund A and figure out, therefore, what nominal monthly interest rate Fund B has to offer. Okay, so let's just change the problem very slightly. And right, let's redo this problem that I just did right here. Move this up a bit. But let's assume Fund B offers instead nominal interest compounded continuously. Okay, so let's get rid of all this here. Well, I'll get rid of this here. So nothing changes for Fund A. Sorry, I need to get rid of this here. Okay, so for Fund B, interest is compounded continuously. So we're asking the question, what does interest compounded continuously have to be to stay competitive with Fund A? So again, we do the exact same thing. We assume the yearly growth for Fund B is the same as the yearly growth for Fund A and figure out what nominal interest rate that corresponds to. Because any smaller nominal interest rate and Fund B will offer less yearly growth than Fund A and hence will not be as competitive. Okay, so right, all we do now is just plug and chug into our formula, assuming I is, again, 0.08322, the yearly effective annual interest rate for Fund A. I kind of maybe cheat a little bit sometimes and kind of say interest, effective annual interest rate and yearly growth synonymously. I mean, they're basically the same thing. It's just, if you have an effective annual interest rate, you add 1 to get the yearly growth. So, and if you have a yearly growth rate, you just subtract 1 to get an effective annual interest rate. So if I kind of interchange the two, it's because they're practically, in some sense, virtually the same thing. Anyway, so right, so the formula here is ln of 1 plus I, and I is 0.08322. And you plug this into a calculator to get 0.7994. Okay. So one point, very practical point for this course that I want to reiterate, I already stated it, is that all 3 answers we got, so in the previous example where Fund B has interest compounded monthly, we got I12 was 0.0802. Here, I infinity is 0.07994. For Fund A, the yearly growth, or rather the yearly effective equivalent effective annual interest rate is 0.08322. These are all very close answers. I mean, they're different enough that when you're doing financial transactions, you still want the better interest rate, or you want, they're not close enough that it doesn't matter, but the point I'm trying to make is they're all fairly close to each other. So if you do a problem like this and you get, answers that are totally off, totally different, you obviously did something wrong. all these different interest rates should be fairly close to each other. If they're not, you did something wrong.
Let's talk about discount. And discount is a very practical alternative way of thinking about present value and right. So the idea behind a discount rate is extremely straightforward. Let's say I have effective annual interest is 7%. What does the present value of 1,000 do in 1 year? Well, we know how to do that. We just plug into the formula. Our present value factor is 1 over 1 plus I, which is 0.93458. So that's going to be $934.58. All right. So instead of thinking about this in terms of a present value factor, it frankly probably makes even more sense to think about this as, well, what percentage did $1,000 lose in 1 year? I don't know. Let's figure it out. So just dump into your percentage changed formula. So you take your starting value minus your ending value, and then divide by 1,000. All right. So really, that's 1 minus 0.9, 1 minus your present value factor times 100. You just cancel out the thousands. 1,000 here, here, and here. Right? And there's a reason why I'm writing it like this, 1 minus your present value factor. And that gives me 6.542%. Okay? And the meaning is, well, it's exactly the percentage that you lost in 1 year. And if you, when you went back 1 year, you lost 6.542%. And, because, well, when you lose 6.542% and you start off with 1,000, you get 934.58. Okay? And we can just continue this logic to see what the present value of 1,000 in 3 years is if the fund loses 6.542% per year. You just keep doing this. We already did 1 year, and we had 934.58. We do the same thing. We take this 934.58, subtract off 6.542% of it. All right, and we do that, we can factor out the 934.58, just like here we factored out the 1,000. And remembering that 934.58 is 1,000 minus 1.06542, we get a minus 1.06542 squared. Do that one more time, and we get 1,000 minus 0.06542 cubed. And this gives us a formula for the present value due in T years if we're given how much the fund loses per year. All right, and that formula is, well, the formula basically, as we've seen, is that money will lose 1 minus your present value factor times 100% per year moved back. Okay, and I'll get to the present value formula, and this is as a percentage. So. All right, so to denote this, we define our discount rate as D is 1 minus your present value factor. And again, just as I said here, as a percentage, that's exactly how much you will lose per year moved back when you're taking present value, when you're discounting money. Okay, and this says, as we've seen in an example, when you figure out what percentage per year moved back money will lose, you convert that to a decimal, 1 minus that decimal, which is D, raised to the t times k gives you the present value of k due in t years. Right? So for example, we just saw the present value of 1,000 due in 3 years is 1,001 minus 0.0652 to the cubed, where the fund loses 6.542% per year. Right? So definitely important formula to remember in terms of the discount rate D. Okay, so we have a bunch of formulas in terms of discount rate. The definition of the discount rate is 1 minus nu. Nu is itself 1 over 1 plus I, so you just simplify 1 minus 1 over 1 plus I. You get I over I plus 1. Should be able to do that, I hope. You get nu is 1 minus d, not a whole lot to say there. You just take this here that I'm circling with my cursor, add nu, subtract d. If you take what I'm circling here and just simply solve for I, you'll get I is d over 1 minus d. If you plug in for d here in terms of I over 1 plus I is 1 minus nu, so solve for I, you get 1 over nu minus 1. So, I mean, if you're in my class, I mean, for assignments, quizzes, and exams, you don't really have to memorize all these formulas, but definitely, if you're taking exam FM, and I hope all of you will take exam FM eventually, you really have to memorize these formulas. There's really no way around it. And I'll probably make this recommendation many times. But just as a blanket recommendation for how to memorize formulas for any actuarial exam, what I like to do is make note cards and just carry around the note cards with you. If you're on the bus, if you're just waiting for something, waiting for someone, if you're at the gym lifting and you take rest breaks. Anytime you have some free time, you just whip them out and just go over your formulas. And if you do that in conjunction with a lot of problems, in no time you'll have these formulas branded into your brain, as I like to say, whether you like it or not. Obviously you would like it, but if you do the two together, I guarantee you, you're going to have these formulas branded into your brain.